Hi everyone, my name is Vitaly and I'm a data scientist at LinkedIn. You might know us as the company that lets your neighbors and family endorse you for stuff they know nothing about. And I'll be talking today about, let's call it, I tried to pick a generic name enough that just a data analysis and kind of the applications of functional programming towards it. Before I start, just a small raise of hands. How many of you are data scientists, data analysis, data whatever, but people will work with data? Wow, that's actually much more than expected. Okay, that's great. So one thing about me, unlike I guess many of the previous speakers, I'm not a Scala guy. I'm not sure I'm even a data guy, but still gonna share my thoughts with you about the subject, and the driver behind this presentation is some frustration I had with some of my colleagues, more of a junior members that are doing some analysis and whatsoever, and they're using, okay, I'll maybe use the terms even though I hate them, big data or small data, but just because they're short, not because I actually think we should use them. And they're doing it, and they're doing it by Excel or SQL or whatever. And then they realize, okay, well, there's so much you can do with Excel or SQL. And then they say, okay, well, I need to probably code something in order to get to the next level of analysis. And they ask me, what should I use? And say, hey, why won't you use Scala? And I say, oh my God, no, it's a functional language. And I said, well, what do you think Excel and SQL are? And I said, yeah, no, I think I'll use Java because it's so easy or whatever. And I guess I come to meetings like this to be among peers. So this is not a talk that is about selling functional programming, because hopefully I'm preaching to the choir. Everyone here, I guess, understands and realizes what are the benefits of functional programming, and you do understand, it's probably why is it better than the other alternatives. But I will still speak about a specific subject, which is for me data analysis, or as we can see here, this is the name of the talk. And just for this talk, and without debating it for too much time, so for this specific talk, when I talk about data, I talk basically about random facts, whether it's some sort of logs or some Internet of Things thing or whatever, but basically it's a set of facts. And here, by me using the word fact, it wasn't accidentally chosen, we can pretty much all agree that facts are in most cases immutable. And in most systems that we data scientists use, they actually are also stored in immutable storage system. One example might be Hadoop. And when I say analysis, I mostly mean math. And when I say math, I really don't mean this complicated machine learning, statistical modeling, blah, blah, blah. I really mean what most data people do 99% of their time, and it's just counting, filtering, aggregating, and other things we do. This, I would love that most of my day will be, a one giant Kaggle computations where the data set is prepared for me, and all I can do is just, try different models and see, plot nice graphs about how the models are able to predict. But again, honestly, most of my day is writing code that just gets data in one form and transform it into another form. And this transformation is pure mathematical transformation, as the way we know it. And the last thing is functional programming. So this is something I took from Wikipedia, which is a programming paradigm that avoids state, mutable data, and side effects. And here is where I find it a little bit funny about, especially when I talk to my math colleagues, is trying to understand the programming paradigm that avoids state immutable data is kind of, you are under the assumption that, well, there is state mutable data in side effects. But if you talk with any mathematician, the concept of side effects is totally strange for them. I don't know how many of you ever, did any math class where you suddenly, solved an equation and that equation had side effects. So and again, it's kind of hard to understand. It's, like I said, I found it pretty funny where in Wikipedia defines functional programming as something that avoids something else, where why do we even assume that the something else is the basis that we should be compared against? So this is kind of my talk about this functional data analysis, or as what it really is just basic math. And I kid you not, it will get very basic. Here are 5 apples. And here, if let's say our brains are kind of neurologically wired, that the fact that the way we know that there are 5 apples there, we don't actually count them one by one. We just see the picture and we recognize the pattern and we see 5 distinct things, and we don't even have to sum them up. Or like my 2-year-old daughter, she actually, even though she can see there's 5 things, because she cannot remember all the numbers all the time, then she actually goes and counts, but it's more for her to remember what the sequence of the integers are, and not actually because she needs help with recognizing there's 5 elements there. But if we're talking to a computer now, any computer, any data structure you will store it in, no matter what it is, will probably, in order to get the sum, you will have to kind of somewhat sequentially go through it and count all the apples. However, there are different ways of doing this, achieving the same result. And here's another way. Still, again, nothing mind-blowing so far. It's just we can actually try and separate and assume there we have 3 people that count these 5 apples, and we tell them, well, you count this part, I'll count this part, and the third person will count that part. And we actually can separate our work among these people. And the question is, interestingly, so why is that possible? Why can we actually, when we are kind of doing the task of counting apples, why can we just easily separate it into into just separate people counting, and then we can somehow aggregate their partial results? Anyone care to take a guess? Yes, exactly, because counting is associative. So this is why we can do it. In case someone, again, doesn't remember this basic math and what associate means, it means that we can basically, and here I use the kind of the curly braces as parentheses, but it doesn't really matter where you put the parentheses, and kind of what will be the order of the execution of this count. We will always get the same exact answer. There will always be 5 apples there, unless we have very bad counters, which can also be. OK, but the question is, how does it help us? And when I mean us, it's me as a data scientist. This associative property, and we kind of mention it briefly. What's so easy when some of the operations or transformations or aggregations I need to do have this wonderful associative property is we can easily parallelize them. And when we, and again, forgive me for using the B word, when we're dealing with big data, or should I say just very, very large amounts of data that cannot be stored on a single machine, it's actually very important that we can do some operations in a parallel way. So how does it all relates to this functional programming? It's one thing I forgot to mention is I'm also, besides my job at LinkedIn, I also contribute the two projects that are started by Twitter. One of them is Scalding, which is this Scala DSL for running MapReduce jobs built on top of Cascading, which is a Java one. And also, but Scalding very much depends on another one, which is kind of less known, but also written in Scala, called Algebird, which is in Twitter, every project has to have some bird in it. So Algebird is, in case you know, right, it's an algebra library built by Twitter. And back to the parallelism part is, okay, so we said we have this wonderful associative property, we can parallelize things, so how can we kind of generalize it besides just counting? And one of the most basic thing, and here I just have to commend myself, I actually did not use the word monoid, so if anyone is actually playing the monoid drinking game, it's not a monoid, it's a semigroup. And the reason why it's a semigroup, because for our specific purposes, at least in how scaling is implemented, we don't actually need zero element. And here we go into like another kind of funny definition that I think most like functional programmers, but I guess math people will get it. Another way, the best way to explain a semigroup to a functional programmer is to say it's a monoid without the zero element. Because apparently that is, and I've tried different explanation, but yes, so, and I think this is the one that people can understand the best. So it's the kind of simplest trait that we can think of. It defines one function, it's a plus, it has two elements, and unfortunately, there is no good way, at least in Scala, to define it in code. But in order for a semigroup to be a real semigroup, the operation has to be associative. Just in case, again, the word associative is a far and distant memory for some of you, some operations are not associative. An example of one can be median. So the medians of other medians is not necessarily the median of the original group. In case, I guess that is still another great example, you can think about it and kind of realize. So this semigroup, in our case, is the very basic integer semigroup that defines plus as, well, surprise, surprise, as the very basic plus operation that we know from, basically elementary math. But yeah, in order to make it kind of interesting, let's not stop at this one. Hopefully we can get to better stuff than explaining after, I guess, 15 minutes of talking that we can, after a PhD in computer science, we know how to sum two integers. Let's try another one. So another example is finding large, here in my example I use 2, but it's finding large K elements in a data set. And this is, again, an operation that is fairly common in, in data analysis. So here are our kind of 6 elements. And one way that people approach this problem, okay, so how do we find the largest 2 elements, is let's sort all of our elements, pretty straightforward, and let's take the top 2, and here we have the top 2 elements. The problem is that this method is not very scalable, and especially when we're talking about, again, large amounts of data. It gets pretty hard to sort all of them, especially when we consider at least at some of the systems, and I think still the kind of common big data processing tool, even though we had a Spark talk before, and Spark is kind of amazing. But if we take Hadoop, for example, the way that Hadoop the way kind of to sort things in Hadoop, if you want a consistent sort, is to get it all into one machine and then sort. It becomes a big, big mess and just not a very scalable way. But the funny thing is, what would happen if I ask you the same question, but instead of finding the largest 2 elements, I would ask you to find the largest 1 element. And here's the cognitive dissonance for me, and it's also kind of a funny observation, is no one here would suggest that I should sort all the elements first. Is that correct? But suddenly, when it becomes 2 elements, then yes, a lot of people, of course none of you guys, but a lot of other people, suggest that we should sort all our elements first to get the second. So why is that? And I guess because we're very much trained, and I guess that goes for our kind of imperative programming background, that the way to find 1 element is to set some element to be this whatever minimum integer or whatever language we use, and traverse every element and assign, and we find this 1 largest element. But when it's 2, then it's gonna get a little bit more complicated. How can we do in a kind of single pass, how we can find the largest 2 elements? Well, we can say, okay, then we can say, instead of using just kind of 1 variable, we can use 2 variables. But again, of course, if we're talking about k, then it's not the best. So in case, we can say, let's use, and here again, so let's use a list, and I'll just get back to it, but list is not the best element. And I'll just show how specifically it's implemented Scala, but there is, again, there is no kind of huge math behind it. But another thing that we would like to do is also to be able, and that we cannot do if we do the sort, we want to do it on separate machines, very similar to how we done before. So we kind of break it, and as you can all guess, it's take a kind of a log number of steps instead of taking the actual, going through the sequences. So how does that work? So there are 2 things here that we need to realize. One is, again, I use the curly braces, but to represent the things we're doing on, let's say, a single machine. And if we're talking kind of Hadoop, then let's say it's at the map stage of Hadoop. But we want, in a single pass, get our largest 2 elements. And one of the ways to do it is to use a priority queue, and you just initialize a priority queue of size k, and then you traverse through the elements with your priority queue and get the largest 2 elements. We can do the same thing on the other machine and get the largest 2 elements, and then we can merge this. So in Algebird, there is a trait that's called aggregator that is exactly to kind of do such kind of transformation. So the aggregator trait has 3 steps. So the first step is called prepare, the second is reduce, and the third one is present. Prepare is basically we have data, let's say, in one form, and we want to transform it into another form, a different one. And as you can see, we want to transform it to something that the reduce function will be applied on. So the reduce function, also you can kind of guess from the name, and if you're somewhat even slightly familiar with the MapReduce paradigm, the prepare will probably kind of map side operation. The reduce is, okay, send all the things that have the same key to the same reducer and perform the reduce operation on it. And present is take the final, and just in case we want it in some different form, we can transform it yet again. It's another kind of a map stage. It's not really another map stage. It's just it happens in the reducer after it's done. But what's nice about this, you can see that the reduce operation has a very familiar signature, and that signature is exactly the same signature the plus operation had of the semigroup. And there is actually, I think in most, when you will write the code, you will find that most of the operations, when we actually want to use this aggregator pattern, we will use it using a monoid, and the reduce operation will be basically calling the plus. So usually how it goes, using the prepare, we map our data into some form of that monoid that we want to use. The reduce operation will just be the plus operation of that monoid and represent as whatever, however we want our input back. Okay, so let's just look at the example of how this might be. Yes, and another. Well, let's first look at it. Okay, so there is just something called a priority queue aggregator. It's also part of algebra. And this is the implementation of if in scalding, and sorry for not elaborating a lot about scalding, but in scalding, when there is a sorted take method, which is basically take the top k element according to some ordering. And what it does underneath is basically calling this priority queue aggregator. And of course, it has slightly more code than that, but on a very, very basic level. And I had to kind of hide a lot of code here. But the prepare is take whatever your input is, create a priority queue that accepts that type, add it to the priority queue as just a single element, and return the queue back. So after applying this on all of our data, or the circles kind of I showed before, instead of each line being, let's say, the circle, each line will be a priority queue of size 1 that has the circle, but of size 1, and sorry, but also I forgot, the priority queue also needs to take an maximum number of elements, but this is in the code that I just decided to leave it out of here. But if you go to algebra, then just look at the priority queue aggregator code, you will see it. But again, the priority queue will have just a single element in it. So the reduce operation, that is just the plus operation. And there is also a kind of in algebra, the nice implicit, which again, I don't know if it's a bad word in this kind of conference, but there is an implicit that whenever you use the plus sign, it actually goes and checks whether there is a semigroup defined on the types that you just define. Sorry, you're using the plus operation on. And if there is a semigroup defined, then it actually will use the semigroup operation of that specific type. So this is actually how the code is written. And you can see that on this L plus R. So the question is how this plus operation works. So we can just look at our final example. Here, if you look at it, let's see if it works. Yes. So we have, we need to somehow combine now two priority queues. One has these two elements and one has these two elements. So one way is just to, define a new priority queue of size 2, if that is what we're interested in, and to basically add all the 4 elements into that single priority queue, and that is what we will have at the end. Another thing is, there is just a slight optimization, but it's not extremely important, that we start with the larger queue if they're sometimes they're not the same size after some operation, but we start with the larger one, and then we add all the elements from the smaller one, and again, at the end, we have the exact right answer. So back to the code, and so the reduce operation is that's just the plus The plus, that is defined on the priority queues that I just defined. And the present is basically, I don't want my results as a queue, I want them as a list, so I can, and usually what people do is actually flatten that list, so I can have all my elements kind of in a nice sequential way. Another kind of a very neat thing to notice about this kind of trick is if you don't know what I'm about to speak and you never use Hadoop in real life, then just ignore what I'm about to say. But if you ever use Hadoop, then Hadoop also has this optimization everyone is talking about. Let's say almost, as much as you can use combiners. So combiners is this reduced stage that happens in the mappers themselves instead of the reducers. So in their infamous word count examples, instead of going through our code and emitting the word dog and sending it to the reducer every time we see it, we can actually count how many times we saw the word dog on a single mapper, and then send it just once with the count. Hopefully, most of you just know what I talk about. The thing with combiners to understand is that we cannot always use combiners, because in order for the combiners to function properly as well, the operation has to be associative. Because if the operation is not associative, we cannot actually use the combiners. Again, median could be an example. But guess what? We are working in a functional language, and we are using functional programming, and we actually define reduce to be a monoid. So hence, it's a great thing that, well, again, as long as we follow the constraint that reduce is an associative operation, it means that scaling will always use combiners by default. And hence, if you just benchmark it versus other applications that do not have this concept, again, like Pig or just other frameworks, even Java one like Crunch or Cascading, they have no way to know from the code that this operation is actually a monoid. And since they have no way to know, you have to explicitly each time say, hey, you know what, I want to use combiners. In scaling, that's not necessary, so it actually gains a very nice productivity gain in terms of how many things we can do. But I should kind of speed up. So monoids. Monoids, we all heard the word, but at least for us data science, it's not about just counting, summing, and min-max. There are very, very basic monoids. But there are some monoids that are fairly sophisticated, and here are just a few examples. On the left side, you can see that this kind of monoids are actually fairly simple, but on the right side, so I mentioned priority queues, moments. Again, moments there's the four or five moments, which is like this average, standard deviation, and skewness, kurtosis, and I think I forgot one. But sorry, yeah, count is one. It's actually all of them are associative. Priority queues I mentioned, Bloom filters. If you don't know, it's like this statistical filtering thing where you can say whether an element exists in a set or not where you only have one type of error, but you don't have on the other hand. But Bloom filters, if you go to their underlines kind of bit arrays that also are associated, we can actually take two Bloom filters and combine. So if now we want to create a Bloom filter out of our entire data set, we can actually create many Bloom filters of size 1 for each of our element in our data set, and then just combine them using a plus. It's not trivial, but it's also not very complicated. It's actually not complicated at all about how I combine Bloom filters and have a correct result. Min hash and hyperlog logs is, again, the sort of variant that also a Bloom filter checks if an element is in a set. Hyperlog log also answers how many unique elements we have in our data set. Also a completely associative operation, and count min sketch
also tell us how many times every element is in a set. Also in kind of statistically with with a very small amount of bits, we can get pretty accurate results. And stochastic gradient descent. But anyway, all of these are monoids, and I, as a data scientist, tremendously enjoy the fact that these operations are associative, because then I can do all of it in a parallel manner, and I don't need to worry about getting the wrong result or the operation taking a lot of time. So here's another meme, monoids everywhere, which I guess can sum up the entire conference, not just my talk. But are there just monoids? So monoids is awesome, and again, not monoid is actually a semigroup, and it has a plus. But as we all learn in elementary math, there are more operations than just a plus. So here is another example, and I'll go pretty fast with it. So we have matrices and matrix multiplication, aka dot product. Again, this is a reminder for people who just don't remember, and it's completely OK not to remember it. The way we multiply two matrices is we take every row element and we multiply it by every element in the row and multiply by every element in the corresponding column, and then we sum all them up. One way to think about this matrix operation, we can define another trait, and I will give you a spoiler in case, well, you know your category theory, probably most of you know it better than mine. That is also known as a ring. But for our demonstrative purposes, ring is basically like a group, which group is a monoid with the negation. Ring also adds multiplication on it. But for the sake of matrix, we actually care about two operations. We have an element-wise operation, and we have the final reduction. That's just how we call it. So element-wise is multiply 1 by 7, 2 by 9, 3 by 11. And the final reduction is just aggregate all these partial products. So again, it's very simple. In the matrix product, if we can define a matrix, and we can define a matrix product to be anything we like, as long as, you know, and we can just give it a ring. And the ring defines, the ring of just a linear algebra defines the element-wise operation as multiplication, and the final reduction as summation. And there is a wonderful matrix API in Scalding that and a lot of time it's very convenient for us to hold our data as a matrix. And if we want to kind of multiply these matrices, this is the very simple ring width that we can provide to the matrix, and that will work. However, that is not, the interesting part is, OK, it's fairly clear what we can do with the kind of trivial integer ring or any numerical ring. Can we think about something else? So another case in data analysis where we use matrices a lot is in graph analysis. And this is, you can see on the left, is another way to represent a graph as this adjacency matrix. And then the number one is, let's say we have edges of basically of size 1. They all have the same length. And we can define a different ring for our matrix operation. What if we define the element-wise operation to be a plus and the final reduction to be a minimum? As you can see, there is a huge spoiler there on the name of the object that what we will get. So again, we have this matrix, and you can already see when we take the matrix and multiply it by itself, we take all the elements and we say, OK, what we want to do is to sum up the row in the column. So if we have now basically a central node that it takes one step to reach it, and it takes one step to reach from that node our target node, then it will take us now 2. So we perform a summation on all the possible ways to reach a certain node in the graph. And when we do when our final reduction step is the minimum, then we'll take the minimum out of all the ways that we have to reach that specific node, and we'll get the shortest path actually in a graph.
And you can check my results. So after a singular iteration of multiplying the matrix by itself, we will actually get a new matrix that looks like that. The point of this example is not to say, OK, this is how you should implement shortest path algorithm in a graph using matrices and like the strings, but just to show that by changing two very simple functions and by saying, OK, a matrix, we can always think about a matrix as this thing that holds some numbers in it. But what if our matrix was a matrix of something else? Would it work? Well, the answer is it would work if we only define the plus and the product operation on that matrix. And if we define it, we can define it in different ways. And one of the ways is, even though the matrix was still an integer, but you can think of a matrix of some random objects that you also have this operation defined on them. It's actually will produce interesting results. And the only abstraction kind of math takes care of everything as long as you give it the basic building block of, OK, what do I do when I take two elements of a matrix? OK, you do what I call here the element-wise operation. So that is hopefully, I don't know if it completely convinced you, but functional programming, or in my version of functional programming, is not promises, futures. It's more very, very basic math. It's just whatever we think about integers, we can do the same about things that are not necessarily integers. And it is the correct way to find kind of the correct way to think about data analysis problems. And kind of speaking from now experience, when we actually tried it and we introduced new members to Scala and this framework, that algebra, we actually gain a huge gain in productivity and just the quality of code people produce. So it does have its benefits, and I suggest everyone to try it. Thank you.